All right, hello everyone. We're going to be talking about section 8.5, which is going to be about probability distributions and the expected value. So the most common way to keep track of an individual outcome of an experiment is to assign a numerical value to each one of the different possible outcomes. So for like example, we can call outcomes X, and then we can assign values of 1, 2, or 3. So in this sense, if we assign these numerical outcomes to assign numerical values to every different outcome, and then all our outcomes are referred to as X, then in some sense the values are going to be random, so X would be considered a random variable. Since we cannot ever really predict an outcome, we can always give it maybe a probability or percentage, what we think it may be. We can never really know, so every time we have an outcome, we can assign it these different values, and then they're essentially going to be random since we don't really know. And so every time we do this, we just get different values of, in this example, 1, 2, or 3. And then once we combine all of these values, X would now be considered a random variable. So basically the accumulation of every single outcome that got assigned a value is now X. All right, so a random variable is a function that assigns a real number to each outcome of an experiment. So that's exactly what we just talked about. So if we have our probability distribution now, it's going to be a table that lists all the possible values of a random variable with corresponding probabilities, and it's going to be called the probability distribution. So we have all the different values, our numerical values that we have assigned our outcomes, and then we have the corresponding probabilities that they will occur. So once we have this, this is called a probability distribution. And that just means that we have a long list or table of values, and we have distributed properties for each one of our outcomes. So the sum of all the probabilities in a probability distribution must equal 1, because the combination of all these outcomes has to equal 100% or 100% of your outcomes. So each one is going to have a different probability, but add it all up, they'll be equal to 1. There's just one probability for every value of the random variable. This is a probability distribution, defines a function called a probability distribution function, or we can just call it a probability function. That's when it's more often called. The information in a probability distribution is often displayed graphically as a special kind of bar graph called a histogram. So we can have these probability distributions, and maybe they're shown in a table, but we really like to show them as histograms because then we get a really nice visual idea of maybe which outcomes have higher probabilities than others. So in figure 8 and 9 here, we see two images. They're both going to be histograms. And so we see on our x-axis, we have 0 to 3. So our options would have been 0, 1, 2, and 3. And then we have our y-axis, which is the probability. So the y-axis is only going to be between 0 and 1, since we can have more than 100%, or we can have more than 1. So our y-axis is going to record the probability of every outcome. So that's what our histograms are going to look like. They also, if you notice, we see that the bar, the kind of middle of the bar is usually where we label our values. So that's why you see here, where's my mouse? Here we go. That's why you see here we have this 0 and it's right in the middle of each bar. And that's just because it's just one value. It's not a range, so we wouldn't put them in between. And they usually have a width of 1, so they almost always have a width of 1, but it really just depends on whatever your values are going to be, whatever your assigned values are. And then they'll have varying heights, of course, because they all have different probabilities. All right, start with our first example. We want to find the probability distribution and draw a histogram for the number of tails showing when 3 coins are flipped. So what we're going to do here is we're going to let X be the random variable. Meaning the number of tails. So X here is going to record our outcomes when we have different numbers of tails, when we flip 3 coins. Then X can be values 0, which means 0 tails, 1 as in 1 tail, 2 as in 2 tails. Oh, we can have 3 tails. And this is to represent the number of tails flipped when flipping 3 coins. So these are all of our outcomes. We can have 0, 1, 2, or 3. We obviously can't have a negative outcome, and we can't have 4 because there's only 3 coins. We can have anything in between. So to find the probability, for each outcome, let's figure out our sample space. So we want to find our sample space. We know that we are going to have 4 different outcomes because we have 0, 1, 2, and 3. So we have 4 different outcomes. Remember, with our sample space, we care about the order. We want to know what order they're going to go in. So we need to find all the different ways that they could be arranged. So we can say, well, we know there are 2 options. 2 options meaning just heads or tails. And 3 coins. So 2 options, 3 coins. So we can say 2 to the 3rd power, which we know is equal to 8. So we can say there will be 8 outcomes. Now we know there's going to be 8 outcomes, but let's find those outcomes. We're going to let little h be heads, and we're going to let little t be tails. So if we want to find all of our different outcomes, we're going to set up our sample space here, which we'll just call S. Say S sample space. So we have S here, and now we just want to think of the different ways that they could be arranged. So let's start with there are 0 tails, which means that we'll have heads, 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 and that's how we'll write it. We'll just write it as basically just one term. So there's no tails, it's all heads. Now we think of, okay, well, what about 1 tail? Well, let's start with 1 tail and 2 heads. Now there's different ways that we can arrange this. And when we do, we could have heads, tails, heads, or we could have heads, heads, tails. And that's going to be the 3 different ways that we can arrange having 1 tail. Now we want to think about 2 tails. So we can say tail, tail, head. Now we can rearrange this. Maybe we'll say tail, head, tail. And then maybe we'll have head, tail, tail. And those are the 3 different ways that we can get 2 tails and 1 head. Now if we want to have 3 tails, there's only one option. It's just going to be tails, tails, tails. And we see here that when we add all these values up, this is 8 outcomes. So we know that this is going to be 8 outcomes. So we want to put our results in our table. So let's put our results in our table. And this is our table here. Our probability distribution of tails, obviously a little table. So we know there's 8 outcomes. And if we think about getting 0 tails, there's only one option when we get 0 tails, and that's when we get heads, heads, heads. And that means that we have one option out of 8 of getting 0 tails. So our probability is going to be 1 divided by 8. Now we can think about the probability of getting just 1 tail. Well, we see there's going to be 3 different options. So let's actually highlight this. So 0, 0 tails. Let's do 1. There's going to be 3. You see there's 3 options in which we can only have 1 tails. We know there's 8 outcomes, so the probability is going to be 3 out of 8. Now we want to think about the probability of getting 2 tails. And we see here that there are 3 options in getting 2 tails. So once again, our probability is 3 divided by 8. And lastly, we want the probability of getting all 3 coins as tails. You see once again there's only one option for that. So our probability is going to be 1 divided by 8. And now remember when we said that each one of our probabilities, when we add them up, have to equal 1. And if they don't equal 1, then that means that we messed up somewhere. And if they do equal 1, then we know that this is most likely correct. So we can just add them up. So we'll say check. We have 1 over 8 plus 3 over 8 plus 3 over 8 plus 1 over 8. We see that's going to be 1 plus 3 over 8 is going to just be 4 divided by 8 plus 3 over 8, 7 divided by 8 plus 1 over 8. That's going to be 8 over 8, which we know is equal to 1. So we know that's right. All right, so now since we have all of our probabilities, and we know the values, let's fill in our histogram. So remember here, we're going to have our x values going to be in the middle of our bars, and then we're going to follow up to the probability. So we see that the probability of 0 tails, we know is going to be 1 divided by 8. We see 1 divided by 8 on our graph here. So we're just going to fill in our box. And there we go. That's our first bar in our histogram. Now we can do our second. So we know that the probability of getting 1 tail out of 3 coins is going to be 3 divided by 8. So let's just put this in our histogram. We see we're going to follow around 1. I'm going to go up to 3 divided by 8. Just color that in as best as we can. Doesn't need to be perfect. You just need to be able to essentially get the idea with your histograms. Now we want to think about, well, 2 tails out of 3 coins. The probability is still going to be 3 over 8, so we're going to have the same value for x equals 2. And we'll just fill that. All right. Then lastly, we want to fill in our histogram here for our value of getting 3 tails out of 3 coins. Once again, we see this is going to have a probability of 1 over 8. So then we fill in our bar. And there we go, and there's our histogram. And we can kind of maybe outline this a little bit just so we know what's what. Fill it in. You can fill them in however you like. You essentially just want to make it clear though, like what's what. Doesn't need to be anything crazy or fancy. All right. And so that is how we create a histogram from our probability distribution. All right. So moving on, we have our expected value. So in working with probability distributions, it's useful to have a concept of the typical or average value that the random variable takes on. So we may not always know the outcome of our next result, but by finding the average, we can make better predictions. So our expected value is pretty much just telling us what the average value is going to be. And if we know the average value, then if we want to make a prediction on maybe what will come next in our outcomes, we'll have a better idea of what it probably will be if we know the average or expected value. So the definition that the book gives is the expected value. Suppose the random variable x can take on the n values of x sub 1, x sub 2, x sub 3, all the way to x sub n, so how many outcomes you have. Also, suppose the probabilities that these values occur are respectively p sub 1, p sub 2, p sub 3, all the way to p sub n. Then the expected value of the random variable is going to be e of x, and that's how we'll signify expected values, is equal to x sub 1 times p sub 1 plus x sub 2 times p sub 2, and then you go until you hit x sub n times p sub n. All right, so let's put this into practice here. We have example 2. So we want to suppose that there's a $5 raffle with prizes worth $1,000, $500, and $250. Assume 1,000 tickets are sold and you purchase 1 ticket. So you want to find your expected payback. So what we're going to do here is we're going to highlight just 2 different methods on how to do this. So for method 1, we can say that the random variable x represents the possible amounts of payback. And we say this because if we spend $5 and we happen to win, let's say, the $250 prize, then our payback is $245 because we spent $5 to enter the raffle. So our payback would be $245. So we see that the amount of payback, which is prize minus amount, or we'll say price of ticket. Price of ticket. Put that in parentheses. All right, so now we know how much our payback is going to be. Then we can say, using this information, we can now construct our probability distribution. All right, so we have this probability distribution of winning now. We have our values of x, which are going to be $995. That would be for the $1,000 prize. So we say $1,000 minus 5. Then we have $495. That would be $500 minus $5. Then we have $245, which we know is $250 minus the initial $5. Then we have our last value, which is just -5. So that's you don't win anything, but you bought a ticket. So now we want to find the probabilities. We know that there was 1,000 tickets sold. if there's 1,000 tickets sold, there's only 3 prizes, $1,000, $500, or $250, and that means that there's only 3 chances of winning. So the chances of getting a $995 payback is going to be 1 divided by 1,000. Because there's only one option, there's only one prize of that value. Then our probability of our payback of $495 is also just going to be 1 divided by 1,000. Since there's only one option of getting that payback. Then lastly, for our payback of $245, same thing. It's only one option. So we get 1 divided by 1,000. If any of these prizes had multiples, then these values would be different. Like if there were 2 $250 prizes, that would end up being 2 divided by 1,000. But since there's only one of each, they're each just 1 divided by 1,000. And what we know that when we add up our probabilities and our probability distribution, we should end up getting the value of 1. Well, we can do that. So if we did, we know that 1 is going to be equal to 1,000 over 1,000. And we know this is equal to 1 divided by 1,000 plus 1 divided by 1,000 plus 1 divided by 1,000 plus, and now let's just say we're already using our value of x, so let's use a different variable. Let's just say v divided by v over 1,000. So when we add these values up, we're going to get 1,000 over 1,000 is equal to 3 divided by 1,000 plus v over 1,000. Now we can subtract our 3 divided by 1,000 and we end up getting that v divided by 1,000 is equal to 997 divided by 1,000. And we get this value. We multiply by 1,000 on each side. And we know that v is 997. And we said that v was divided by 1,000, so we know our value here, our probability of getting -$5 or spending $5 on a ticket not winning, is going to be 997 divided by 1,000. All right, so now we have all of our probabilities. And then we can say that, let me see, okay, we have some. The expected payback of a person buying one ticket is, and what we're going to do here is we're going to use this definition that we have of expected value, which we have our different outcomes multiplied by their probabilities. So if we do that, then we have our x, which is our outcomes, and then we have p of x, which is their probabilities. So we can say that this is like saying x sub 1, x sub 2, x sub 3, and x sub 4. Then this is like saying p sub 1, p sub 2, p sub 3, and p sub 4. So then using our definition, we just multiply these values together. So we have x sub 1, which is 995, times p sub 1, which is 1 divided by 1,000. Then we have our second value, x sub 2, which is 495 multiplied by 1 divided by 1,000. And we have our x sub 3, which is 245 multiplied by 1 divided by 1,000. And then we have our final answer here, which is going to be, and we're always adding, so even though it's -5, we're going to add -5 times 997 divided by 1,000. So we can calculate this value, and what we end up getting is going to be 995 divided by 1,000 plus 495 divided by 1,000 plus 245 divided by 1,000, and then we're going to have plus negative sorry, I had to calculate that value. I only had the final answer. So it's going to be 995 divided by 1,000 plus 495 divided by 1,000 plus 245 divided by 1,000 plus negative 4,985 divided by 1,000. So we add all of these values up, and we end up getting negative 3,250 divided by 1,000. Once we divide this value by 1,000, this is going to give us negative 3.25. Since we're talking about money in this case, we know this is going to be the same as saying, I'm just going to write a big slash. This isn't divide, just separating this. Or else just write this. Or we're going to be losing $3.25 on average. So this is saying on average. Now we know that this is actually not a possibility since you pay $5 for a ticket and either you win or you don't. But this is just to say that on average, every time you buy a ticket, you're really just going to lose $3.25. So to sum it up here, we say we know it's not possible to lose exactly $3.25. This just means if you bought tickets to a lot of raffles for a long period of time, you would lose $3.25 on average. So this just means if you're repeating this process for a very long period of time, this is going to be kind of your on average. So this means that on occasion you'll win, but most of the time you probably won't. So you're really going to be losing money in the end. All right, so now we have method 2, since there's 2 methods to do these types of problems. So we can say another way to calculate expected value is to just calculate the expected amount 1 and then subtract the cost of the ticket. So we know that, and we're going to be finding our expected value. We're still going to be multiplying our outcomes by their probabilities. It's just that in the end, we'll just subtract the price of our ticket. So how we do this is saying that we know that the amount won is $1,000 with, and we're going to say P of X equal to 1 over 1,000, $500 with P of X equal 1 divided by 1,000. $250 with probability of X equaling to 1 over 1,000. And $0. So in this case, we're not doing -5, since we're not thinking about the payback, we're just thinking the actual amount that we win. $0 being 997 divided by 1,000. So these are our probabilities with our amounts that we could possibly win. Then the expected payback for a person buying a ticket will be, and now we're going to do essentially the same thing. We're going to do the exact same formulation of an expected value, which is still x1 times p sub 1. So we're going to have 1,000 times 1 over 1,000 plus x sub 2 times p sub 2, so 500. So not 5,000, 500 times 1 over 1,000. Then we have x sub 3 and p sub 3, so 250 times 1 over 1,000. And then we have our chances of winning $0, which is 997 divided by 1,000. All right, so we have all of our values here. We have all the amounts that we could possibly win. So now we need to subtract the amount that we paid for the ticket. The amount that we paid for the ticket is not going to be divided by 1,000, because that would mean that we would be paying an incredibly small amount for a ticket. So our price of our ticket we know was actually $5, so that's going to be the only whole number. Then when we actually calculate these values, we know this is going to be 1,000 divided by 1,000 plus 500 divided by 1,000 plus 250 divided by 1,000 plus 0, since we know that's just going to be 0, minus 5, which we know 5 is pretty much the same thing as saying 5,000 divided by 1,000. So if we kind of, that's 250. If we calculate this value, this is pretty much going to be 1,750 divided by 1,000 minus 5,000 divided by 1,000. And this is going to give us, once again, negative 3,250 divided by 1,000, or negative $3.25, or losing $3.25. So these are two different methods that we could really use to calculate our expected value, and we see it's going to be the exact same answer. So we can use either method when calculating expected value. All right. Just to note, the expected value of a random variable may be a number that can't occur in any one trial of the experiment. So this is to say, or just to reiterate, the fact that our expected value may not be an actual answer. You can't lose $3.25 if you buy one ticket in one raffle, because that's not an option. So once again, just remember that your expected value doesn't have to actually be one of the options. It's just on average, which means that if you're doing this a lot for a long period of time, on average, how much money will you be losing? So it's important to remember that fact. All right, now for example 3. We have every day Donna and Jackie flip a coin to see who buys coffee. It's going to be $2 a cup. One tosses and one guesses, and if the one who guesses is correct, then the one who tossed pays for the coffee. So if one person tosses and the other person is guessing while you're tossing, if they guess right, the other person pays. If the one who guesses it wrong, so if someone got it wrong, then the other person pays for the coffee. Or whoever tossed the coin then would not have to pay for the coffee. The person who guessed wrong pays for the coffee. So we want to find Jackie's expected payback. So we're going to assume an honest coin is tossed. By honest coin, we pretty much just mean that every time you toss it, you have a 50% chance of getting heads, 50% chance of getting tails. It's not like weighted differently or anything like that. So then Donna is going to toss the coin. And Jackie guesses the outcome. Then we can make a table for the possible results. Okay, here's going to be our table. So, starting with our results of the toss. So let's say, for example, and this can be written anyway. This is just basically an example. So we're saying that the result of the toss was that the first toss was a heads, the second toss was a heads, the third toss was a tails, and the fourth toss was a tails. Then we say that when Jackie guessed, on her first guess, she guessed heads. On her second guess, she guessed tails. On her third guess, she guessed heads. And on her fourth guess, she guessed tails. So now we just need to record if her guesses won or not. So we see that our very first result here, she guessed a heads and the outcome was heads. So yes, her guess won. Then on the second result, or a second outcome, it was a heads, but Jackie guessed tails. So we say no, she did not win. Then on our third toss, it was a tails, and Jackie guessed heads, so she did not win again. And then on the last outcome, the toss was a tails, and she guessed tails, so she got that guess right. Now we need to find the probability of her guessing each one of these correct. Now we see that there's 4 outcomes, and our probability of whether she's going to guess it right or not is essentially 50-50, but if we think here, there's going to be 4 different options for each occurrence. So let's say for our first example, on our very first outcome, so this very first column where we toss the heads and she guessed heads. So that's one option. Another option would be that they tossed heads and she guessed tails. So now that's 2 options. And another option could be that they tossed tails and she guessed heads. That'd be 3 options. And then another result would be that she tossed tails and then Jackie guessed tails. So that would be 4 different options on one outcome. So, but the probability of getting it right, or getting it right with the correct toss, we know that's only going to be one outcome. You can only guess heads right once. So this probability is going to have 1 divided by 4. And we see that it's the same thing for each one of these outcomes. So they're each going to have a probability of 1 divided by 4. Then we know when we add 1 divided by 1/4 together, we know that's going to be 1. So we can assume that this is correct. Then, okay, so we have some we can say Jackie wins a $2 cup of coffee when the result and guess match. Then she loses a $2 cup of coffee when the results and her guess doesn't match. Then the expected payback will be, and then we want to write our expected value here. So we can say that the outcome of her winning, it will be $2. So let's say a win is +2, lose is going to be -2. So our very first outcome, we saw that she did win. So she won a $2 cup of coffee, and the probability of winning was 1/4. So for our first outcome, we have 2 times 1/4. Then on her second outcome, she did not guess right, so she lost $2, or she lost her $2 cup of coffee, and the probability was still 1/4. Then, on her third try, we saw that she guessed wrong again, so she lost her $2 cup of coffee with the probability of being 1/4. Then on her final try, she did get it right, so she won a $2 cup of coffee with the probability still being 1/4. So we can pretty much assume from looking at it directly that we're going to get a value of 0. As we see, there's one positive version and one negative version to cancel out, but even if we add all of these values up, we see our final answer is going to be equal to 0. So this means that in the long run, this implies that Jackie neither wins or loses. It just means that if she repeated this experiment multiple times, in the end, you'd see on average that she doesn't win anything, but she also doesn't lose anything. I just want to go back really fast and just solidify the idea of the probability being 1/4. So let's say probability equal to 1/4. Since 4 different options for each outcome. And we see that's going to be heads, 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 tails, tails, heads, or tails, tails. So that means that the toss could have been heads and she had guessed heads, or it could have been heads and she guessed tails, or it could have been tails and she guessed heads, or it could have been tails and she guessed tails. So let's just put that in a little box. So that's why the probability is 1/4 and it's not 1/2. All right, and then once we see in the long run, she doesn't win or lose, and that's really just because a coin is really going to be 50%. So every time you are tossing it, you really have an equal chance of either getting it right or getting it wrong. So a game with an expected value of 0 is called a fair game, and this is like an example 3. So by saying fair game, it just means that, you know, we had a fair coin or you have fair dice, which means that each outcome is equally likely. So an example, casinos do not play fair games, or else it wouldn't make any money. So casinos don't play fair games. They play very, very unfair games. So then they can make money and they get you to keep spending money. So that's how they get you. So for our expected value for binomial probability, so this is just a definition that we use to say that for binomial probability, our expected value is just equal to n times p. So in other words, the expected number of successes is the number of trials times the probability of success in each trial. So for an example, if 79.4% of people earning bachelor's degrees in 2011 to 2012 are female, and if we take a sample of 5 people earning bachelor's degrees, we would expect that 79.4% of the sample should be female. Thus, this means 5 times the probability of someone being female in this group, and we end up with 3.790. So we say on average 3.7, I think I flipped the numbers here. Yes, it should be 970. There we go. Actually, I flipped that. So it should be 3.970. So on average, 3.970 of the people in the sample, 5 will be female. Obviously, we know we can't have 3.97 people. So this just means, once again, that in the long run, if we took many, many samples of 5 people over a long period of time, on average, we would have 3.97 people out of the 5 be female. So for our expected value for binomial probability, this just allows us to take whatever the percentage of success out of the number of trials, or our probability of success, and then multiply it by like our number of trials. So in our case, we had our percentage of success was 79.4, and then we had 5 people. So 79.4 times 5. All right, so let's do some examples here. So example 4, which is going to be your turn, number 5. We want to find the expected number of girls in a family of a dozen children. And by family of a dozen children, we mean there's just a dozen children in the family. So we're not counting the parents. Okay, so we're going to assume that the probability of having a girl is 1/2, or 50%. So we know that when the mother gives birth, she'll either have a boy or a girl, and it would be 50% each, or a probability of 1/2. And we're just going to assume this probability. Then, using our formula here of expected value for binomial probability, we're going to assume, or we will set, not assume, n equal to 12, since we know there's a dozen children. So our n is equal to 12. And our probability is 1/2. So using our formula, we get the expected number of girls is going to be equal to n times p, or 12 times 1/2. 12 times 1/2 is just going to be 12 divided by 2, which is equal to 6. So we can say, out of a family, we'll say with 12 children, we expect 6 of them to be girls. So our definition of expected value for binomial probability is very straightforward. It's pretty much what's the probability of success, or the probability of whatever we want, times a number of trials, or in this case, a number of children. So if we know that having a girl is about 50% or 1/2, there's 12 children, 1/2 times 12, 6. So we would say on average, there should be 6 girls in a family with 12 children. All right, then for our last example, example 5 here. A local used car dealer gets complaints about his cars as shown in the table below. Find the expected number of complaints per day. So we have the number of complaints per day and then the probability. So the probability of having 0 complaints in a day is 0.02. That's very low. So number of 1 complaint in a day is 0.06. 2 complaints in a day is 0.16. 3 complaints in a day is 0.25. 4 complaints in a day is 0.32. 5 complaints in a day is 0.13. And 6 complaints in a day is 0.06. So we see definitely the number of having 4 complaints in a day has the highest probability. But what we're going to do is just use our expected value equation. So we see here x sub 1 is pretty much, or sorry, 0 is pretty much x sub 1. 1 is pretty much x sub 2. 2 is pretty much x sub 3. 3 is pretty much x sub 4. 4 is x sub 5, x sub 6, and x sub 7. So this means that these probabilities are p sub 1, p sub 2, p sub 3, p sub 4, p sub 5, p sub 6, and p sub 7. And now we just get to use our formula, our original formula for expected value. So we'll say we'll use a formula for expected value. So even though we just learned the definition for the expected value for binomial probability, when we're given charts like these, it's best to just use the original formula for expected value since we know what it's going to be. In cases where we just have pretty much just a number of trial and 1%, that's when we want to use the binomial probability because we don't have a whole range of experiments to draw from. But we do here, and we want to find the overall average. So we'll just use our regular expected value formula, which we know was the expected value is equal to x sub 1 times p sub 1 plus x sub 2 times p sub 2 plus, and then we go until our last trial or our last outcome, which would be x sub n times p sub n, which in our case is going to be x sub 7 times p sub 7. All right, so we're going to use our equation here, or our formula. So we'll just have e of x is equal to, and then we have 0 times 0.02 plus 1 times 0.06 plus 2 times 0.16 plus 3 times 0.25 plus 4 times 0.32 plus 5 times 0.13 plus 6 times 0.06. Then all we need to do is multiply these values and add them all up. So I highly suggest you do this on your own, and you should end up getting 3.42. So this is going to tell us, on average, does he have a name? No, just the local car dealer. So on average, the local car dealer will receive about 3.42 complaints a day. So that's how we would find the number of expected complaints per day. And we obviously see that you cannot have 3.2 or 3.42 complaints a day, but we know that over a long span of time, this is on average how many complaints we would get a day. All right, so that concludes our section on probability distributions and expected values. So as always, if you ever have any questions or anything, feel free to send me an email, submit an anonymous question to our anonymous question form, or you can pop into my office hours at any time. All right, I will see you all virtually later.